Okay, science time. Today we're talking about fields. Fields. This is Farmer Joe's favorite science lesson. What's a field? We use the word field in several different ways. Oops, this needs to be adjusted just a little bit. Okay. We use the word fields in several different ways. Hey, let me tell you a joke. This is going to be great because this video has a joke in it. Why did Farmer Joe win an award? You already know. Jim, you already know. Answer it. Because he was... You know it. You know this joke. Why did Farmer Joe win an award? Because he was outstanding in his field. He was outstanding in his field. Isn't that funny? We use the word field. Okay, and that joke highlights two of the ways that we use the word field. I'm not going to write these down because you already know what a field is in terms of an area of land used probably for farming, for production. There could also be, we could have an industrial field, so that would be used for production. We also use the word field to mean an area of learning or expertise, an area of expertise. So when the joke there is that he's outstanding in his field, he's both out there standing in his field, but he's also outstanding, really good. He's really good in his field of work or study or whatever. So those are two ways that we use field. And we use it in another way in science. We use it in this way that we mean, what is field? You were asked to define field for your bell work. I wish someone else would tell me what it is. I wish everyone would have their notes out because it'd be really important to take notes on this. Someone define the word field for me from your bell work.
A field is the area in which a field force can affect something.
Okay, yeah. That seems really like you got it straight from the text. Let me hear that in your own words, someone else. That is right. I'm not saying that's not right. Oh, that is in your own word. That's really good then. Nice. An area around which a field force can, you said affect something. I'm going to do this. Area and field force. These are going to be our kind of our main topics for the lesson. What's area in math? If I wanted to find the area of a Cheez-It in math, let me draw a life-size Cheez-It here. Yeah, we have the length of the Cheez-It and the width of the Cheez-It. And we would multiply those to find the area. The area of Cheez-It. Could we do that? Let's do it right now. Area equals length times width. Area equals, let's say for a Cheez-It, it's 1.5 centimeters by 1.5 centimeters. Area equals, what's 1.5 times 1.5? Maybe I made the math too hard. Let's do 2 centimeters by 2 centimeters. It's probably more accurate anyway. Area, in this case? No, it's not 4. It's 4. No, it's not 4 centimeters. It's 4 centimeters squared. 4 centimeters squared. So area is of a two-dimensional object in mathematics. But is that right for a field force? No. What is it in reality? A field force acts in not 2 dimensions like area. No. 3 dimensions. So it's really more of a volume. Area might be a word that's okay. It's a volume. Area might be a word that's okay to use in our common parlance for this, but scientifically it's a volume. It's because it's in 3 dimensions. In fact, one of the misconceptions that the book points out that I should teach you about is that the people oftentimes misconceive, because a lot of times we think of fields or we diagram fields in 2 dimensions. People think they are in 2 dimensions, but in actuality they're in 3 dimensions. Really, I think an excellent example the book gives is this kind of metaphorical idea of a stink field. Yeah, do you know? Stink, garbage. Let's say, have you ever been to someone's house and they don't pick up the leavings of their dog in the yard and the whole yard just smells like that? Or worse, sometimes this happens. I've been in a few houses where that's inside. Have you ever been in a situation like, not the latter, but have you ever been in a situation where you smell Dog feces. Feces. Yeah, you have. And you know, like your instinct even. Let's instead of drawing that disgusting thing, let's pretend this is applying to that you have a magic dog that its ejecta is chocolate bar. So here I'm going to draw a chocolate bar. Now this is not something disgusting. This is a chocolate bar. I'm going to write Kit Kat on it so that you know you have a magic dog. I would never, because I'm a professional, I would never draw a diagram of the ejected matter from a dog. But I would draw a chocolate bar. And we're going to pretend that this chocolate bar has a very, very, has a distinct and a large smell. Now, you as a human being, you guys are all human beings, right? You humans, this is how you generally stand. You human beings know that if you, for whatever reason, don't like the smell of this chocolate bar, what do?
You walk away from the chocolate.
Yeah. So here we have.
Or you pick it up.
Here we have. Oh yeah.
Throw the chocolate bar away.
Oh, he has to have a villager nose. Nice. Wait, let me give this one a villager nose too. They really look like Squidward's thing. They look like Bold and Brash here. But anyway, which of these two Bold is? This one's called Bold, and this one's called Brash. Which of Bold and Brash is experiencing a stronger effect of the steam field? Brash does. So we know that the strength of a field diminishes the further we get from the source. Let's write that down. The strength of a field diminishes the further we get from the source. What else could change about this? Well, what if instead of 1 candy bar from your magic dog, 7 candy bars from the magic dog? Oh wait, I think that actually has. I think it's called a big cat, isn't it? King cat. King cat. Big cat. Bobcat. So now, if we think now instead of which one, Bold or Brash, if we think of just Brash, in which instance did Brash experience a stronger effect from the stink field? When there was 1 chocolate bar, or when there are 7 chocolate bars? 7, obviously. So it also, the strength of a field diminishes the further we get from the source, but it also, the strength of a field depends on the, let's put the magnitude of the source 2. Mathematically, we express this as this. F sub g, the force of gravity, equals capital G m1 m2 over r squared, and F sub E, the electromagnetic force, equals capital K Q1 Q2 over r squared. Do you see a similarity? These seem mathematically complicated to you because, well, you're just little boys. You don't understand anything about math. But you're just little boys. But do you see similarities between these two equations? This one is the equation for universal gravitation. This is the equation for gravity in the universe. This one is the equation for electromagnetism. Do you see similarities between these? Well, in both cases, they depend on this capital letter at the front. They depend on some constant, the strength of the force itself. Remember, there are 4 fundamental forces of the universe. Did we talk about these already? The strong nuclear force, electromagnetism, the weak nuclear force, and gravity. And the strength, the variable strength, not variable, but the varied strengths of those forces is given by this constant. In both cases, we're calculating a what? Force. So, is the stink field in reality, is it a force field? Does the stink actually put an actual force, does it put a push or a pull on Bold or Brash? No. No, it might make them want to leave, but it's more of a metaphorical force field. But they both depend, both forces, which put a real physical push or pull on an object, depend on the strength of the force field itself, which is a set constant for the universe. The entire universe has the same constant for these two different things. It's not that these two aren't the same as each other, but throughout the universe, G is always the same, as far as we know. And throughout the universe, K is always the same, as far as we know. Now, what is the force? Great joke, Streety. What does the force of gravity depend on? Let's look at these 3 things. What does the force of gravity depend on? What's M, probably? We had talked about this one before. You should know this. M&M, since we're already talking about chocolate, no. What's the M stand for? We already talked about this equation this year. No, this is the force of gravity. Say it again, Mason. Mass. It depends on the mass of the object falling? No. The mass of both the object falling and, in the case of our marker dropping, which go back to our classic example from this class, depends not only on the mass of the object falling, but also on the mass of the object to which it is attracted. In this case, no, the Earth. Remember your old girl, the thick Earth? What else does it depend on? What is this R squared? Sometimes we use R, sometimes we use D. In either case, it can be D. No, it's either, the R was radius, the D is, what else does it depend on? No? Good guess, though.
Decrease.
No? What else does it depend on? If everywhere in the universe, where I take this marker, it will be attracted to Earth the same amount? Distance. It's the distance between them. The distance between their points of mass. So, in this one, it depends on the two masses and the distance between them squared. And in this one, it depends on the two, Q is the mathematical and scientific symbol for charge. It depends on the two charges and the distance between them. But do you see similarities in these equations? In both cases, it depends on the magnitude of the object and the distance between them, multiplied by some constant. And you can see, since D is on the bottom in both cases, the further away we get, the more the force field decreases, and it decreases by the square. What's another, we have talked about now, these are the two field forces that we are going to talk about. We have gravity and electromagnetism. Since this is electromagnetism, not just electricity, but electromagnetism, does this apply to the static effect of that balloon that I had rubbed on my head in the last lesson? Yeah, of course, that's static electricity. Does it apply to this magnet? Yeah, because remember, we kind of in our minds differentiate between electricity and magnetism, but in reality, they're one force, electromagnetism. Unlike masses, charges can also be negative. They can be negative or positive. What happens, remind me, this is a review, but what happens when two negative charges come near to each other? They repel. What happens when two opposite charges, one positive and one negative, come to each other? They attract. Ooh, this is really dangerous. I'm going to hold that in a different hand. This is already covered in iron filings.
Yeah, actually, I don't want to talk about it.
Oh yeah, what? You don't even know what's going on here. It's actually the North Pole. It's actually like this. The North Pole. I don't know. It doesn't matter which one's which, but the North Pole's this way, and the South Pole's on the bottom half of this. And so I'm really it's really stuck to that side, but really repels the. It's a really strong magnet, but its magnetic domains are kind of all mixed up. Yeah, they're all over the place. It's not just straight up north and south like this one is. Anyway, so we have magnets here, and they, depending on how I orient them, they will either repel or they will attract. So they're repelling right now, and then it'll reorient itself because this magnet's pretty strong, and then it'll switch it so it's attracting. It doesn't actually switch the magnetic field, let me be clear. What it's doing is it's moving this magnet. I can feel it doing it. It's moving this magnet so it lines up with the other pole so it'll attract instead. I'm not going to drop these because one of them is expensive and the other one will damage the floor. But if I were to drop this, what kind of force exists between the marker and planet Earth? Gravity. Yeah, it's an attractive force. Gravity is always attractive. Electromagnetism, because these can be positive or negative, can be either attractive or repulsive. So you understand that the gravitational field, unlike area, these actually exist in 3 dimensions. So we have bold and brash here, and let's say we also have, what's another thing that might line up with bold and brash? Belongs in the trash. So we have belongs in the trash right here, right? This is belongs in the trash. Who's experiencing the greatest effect of the stink field? Belongs in the trash, because it's in 3 dimensions. That is, it's not just in this 2-dimensional circles out from the stink field, but it's in a 3-dimensional sphere out from the stink field. Let me see if I can diagram that for you. I have here my large magnetic field demonstrator, MGF-DO3. And I have, so this thing has, I'm going to try to do this on the camera too, and you guys can see it okay, probably better even if I hold it up. So I'm going to mix it up a little so that what it is it's iron filings in some neutral oil. So here I have iron filings in some neutral oil, and if I bring my magnet, if I bring my magnet close to it, you can hopefully see, use a small one, yeah. You can hopefully see. Now what I'm going to try to do is show this to the camera after I've held it here. You can see it's kind of grouped itself. You can't see because I'm not holding it, right? I'm not good. Let me get someone's test to put behind this. Come on, baby. We're not actually on the... There we go. Okay, you can see it. My finger's in the way. There we go. Okay, so I have the magnet behind it, and you can see, if I even hold it at all, you can see the magnet has gathered the iron filings to it in, hopefully you can tell, no, the glare is too bad, in 3 dimensions, but you can kind of, if you look at this from the side, oof, you can kind of see that they stick out. So let me draw this from 2 different angles to try this. Maybe this demonstration was a failure, but what I've tried to demonstrate there is that if we have the magnet, which I should draw in red, you see this okay? You can really see actually none of this on the board okay. The iron filings kind of gather in a little like, oh, I don't know, like a sunburst around the ends of it like this. And then if you look at it from the side, you can see they gather in the same way as kind of like a little sunburst. Around that. Well, because we're pretending that it's within there. I mean, like if in reality it would just be the bottom part probably, but what we infer is that the field lines actually go around it like this. That the magnetic field is the strongest. The magnetic field is the strongest nearest the poles, but it still exists around here. In fact, technically, just like the force of gravity is universal, technically the magnetic field is interacting with particles as far away as me, just so weakly that they can't move even the tiniest little subatomic particle. That's how, actually, the Earth has its own, in addition to its own really quite strong gravitational field, it has a quite strong electromagnetic field. That's what compasses line up to. You know, a compass is actually a little magnet floating in water, and it lines up with Earth's magnetic field. Let me see if this will... If I had this on a floater, the strong magnet actually does orient itself if you can get this on something that will float it. This doesn't float in water, but if you get it on like a paper plate and put it in water, this magnet will orient itself with Earth's magnetic field. This one may not, but a lot of times what we will do, or what we used to do when I used to give people labs to do instead of letting you think of your own, is I would have people magnetize a needle. You get a needle and you'd rub it on a magnet so that the needle would be magnetic. You'd put that on a sticky note, have that flow in water, and the needle would orient itself with Earth's magnetic pole. Here I have a baggie of iron filings. I'm really bad at showing things to the camera. Here I have a baggie of iron filings, and I've now, you can see, I hope, it just like kind of enveloped the magnet because it works in 3 dimensions, right? It's like it's going all the way around the magnet because it works in 3 dimensions. The field force works in, now it's just, it looks like I just wadded up the, you can see it looks almost like it ate it. Something I was really hopeful about from your lab, Mason, that Tristan and you did, was that you would make that slime into magnetic slime by putting some iron filings in it and then see how it reacts to the magnet. I think that would have been really cool.
Mason has no idea what happened.
So this is all to meet the objective. Oops. To meet the objective, which is, would you please read me the objective, Zach? Oh no. Hey, diagram field forces, and I want you, hey, someone needs to get me a rag. You know the rags I use, they're in the top drawer of that green cabinet. But so we're, in attempting to diagram field forces, we show that these forces, and what kind of, according to the first chapter of our book, are these contact or non-contact forces?
Contact.
Let's try again.
Non-contact.
Non-contact, because remember, even though it obviously it does provide a force in contact, but it also provides a force when it's not in contact. Remember, this one should work pretty well on the whiteboard. If I drop it, even though it's not actually touching the board yet, So I'm going to drop it. You can't really see this from the side, neither you nor the camera, but trust me that I'm dropping this from about 6 inches away from the board, and it zooms right to it. So even though it's not touching the board, it's still being acted on by the board. Thanks. So the objective was to diagram field forces. Do you have questions about diagramming field forces?
No, sir.
What's a field force?
An area around a
Well,
object.
the field is the area around the object, but what's a field force?
Field force is the object.
No.
Well, it's like the force acting on
Yeah, it's a force that acts in 3 dimensions
3 dimensions around
around a source,
the source.
but
That affects things.
in a non-contact way, because these would still work. The field, you should know, the field is not working through the air. Like the air is here as like a bystander. The air isn't making the field work, unlike sound. Sound works by way of the air, but these work through the air, but not because of the air. All this stuff would still work. The whole lecture would work in the absence of air, except I would suffocate and you wouldn't be able to hear the things I'm saying. But all of this, which you already can't, but all of this works in space. They work in 3-dimensional space.
Joe, wake up. There's no time for nothing.
Do you have questions about field forces at all?
No, sir.
We might as well talk about electromagnets just a little bit, since that's what your lesson 4 is. But electromagnets are basically a way that we can use the concepts of current electricity that we talked about in the last lesson to cause a magnetic field. And the basics of electromagnets are, and we mentioned this before, but anytime we have a current flowing, we can use the right hand rule. Remember, you take your little right hand, take it. Take the right hand. Take it. Good. The thumb of only your right hand, put your left hand away. The thumb of your right hand, if the current is going in the direction of your thumb, a magnetic field will always be present around that current in the direction of your fingers. So it curls around. So like if you have a current in a wire, in a purple wire, and the current is going in this direction, well, I can use my right hand rule to tell me that the magnetic field will be going around it in that direction. In 3 dimensions. The electromagnetic force is always in 3 dimensions. And so the current going that way makes an electric field going, or makes a magnetic field going this way. And if we wrap that current around a paramagnetic material, probably not a pencil wouldn't work because that's diamagnetic, but an iron rod, not a magnet, but just a plain iron rod with its magnetic domains non-aligned. If we wrap this current-carrying wire around that magnetic rod, that makes that rod magnetic. It generates a magnetic field, which will align the magnetic domains in the iron rod, making the magnet work as, or making the iron work as a magnet. And only when current is passing through it. If we turn the current off, it's no longer magnetic. So it's very useful for things like people in my front yard picking up nails after they do our siding. You know, because you drive they drive an electromagnet around, pick up all the nails while it's on, hold it over the dumpster, turn it off, and all the nails just fall out because of the force of gravity. Electromagnets. Do you have questions about field forces or electromagnets? Do you have questions about Bold and Brash? Bye.
You need to make a 3D version of them.
Bye. Bye. I wanted to go. Half the video is just me trying to get the video to stop. Maybe my teacup is in the way.
Evil teacup. There, it still didn't work.
It's there. It still didn't work. I'm going to have to get closer. Maybe this thing's running out of batteries.
You need to make a 3D.
The electric field, actually, the electromagnetic radiation field that is allowing my keyboard, my wireless keyboard to work, it's getting a little bit weaker.